by 2030, 60% of 8 billion people will reside in urban centers, requiring $16 trillion in construction output. This construction and operations of buildings will contribute to over 40% of total carbon emissions. We are here tonight to understand how to reduce carbon emissions from new construction by helping decision makers better understand how to account for carbon in their new construction projects. This slide shows the two types of carbon emissions with the example of a building which is in the middle of the diagram. On the left are emissions associated with the building's operation and maintenance, such as lighting and heating. These are known as operational carbon. On the right are emissions associated with building materials, such as steel and concrete. These are known as embedded carbon. Our client, the Port of Seattle, is interested in understanding the feasibility of measuring embedded carbon in their new and upcoming construction projects. So the Port of Seattle is they have maritime and aviation operations in King County, Washington, and they own and operate the Seattle-Tacoma International Airport, SeaTac for short. Guided by environmental stewardship and strong sustainability goals, they wish to transition SeaTac into one of North America's most greenest and energy-efficient airports. For this, they created the Sustainable Airports Master Plan to guide the development of 30 new capital projects that will accommodate over 66 million people by 2034. SeaTac is already reducing their operational carbon by using energy efficiency and renewable energy. However, there is a huge potential in addressing their embedded carbon that will improve their overall carbon footprint. This image here is a rendering of a proposed new arrivals international terminal at SeaTac. New construction projects such as this will require using a wide range of material, including 3 materials that are key in airport construction. These materials are concrete, steel, and asphalt. Our project specifically looked at the embedded carbon in these 3 materials. To illustrate our approach, we look at the example of concrete. Concrete is made up of 4 components: air, cement, water, and aggregates that include sand and stone. This diagram here shows a typical life cycle associated with concrete. It has 4 steps, starting from material extraction to transportation to manufacturing and finally installation. So each component of concrete goes through this life cycle, emitting a certain amount of carbon at each step. The value that represents the amount of carbon emitted is known as an emission factor. And an emission factor is important because it is an industry benchmark used to compare the carbon emission from materials from different manufacturers. Emission factors such as these are widely documented in Environmental Product Declarations, EPDs for short. Now, an EPD is like a nutritional label for a material, stating what the material is made of and the corresponding carbon emissions. All EPDs are verified by third-party certifiers. This diagram here is not an actual EPD, but a graphical representation to help us visualize the components and contents of an EPD. EPDs are issued by the respective material manufacturers, and they are the most extensively cited sources used in other emission factor sources such as generic databases and research reports. This is why we base the bulk of our research on emission factors available in EPDs. Now, circling back to the example of concrete, this slide shows emission factors for the same type of concrete from different manufacturers and their EPDs. So here we see that the concrete used is 3,000, the strength of the concrete is 3,000 psi. Ideally, similarly located manufacturers with similar manufacturing processes should produce similar emission factors for per unit concrete. However, our research shows otherwise. This table here shows a variation in the emission factors noted, ranging from 286 to 443 kilograms CO2 equivalent or CO2e per unit concrete. This variation means that the emission factors are either being underestimated or overestimated. Our client is aware of that such variations exist, but they then wanted to know if these emission factors can be used to accurately measure embedded carbon. Specifically, they wanted to understand the reason behind these variations. Our research brought up two major reasons for this variation. The first reason for variation is using data from different sources such as EPDs, generic databases, and research reports. This leads to three issues in the data quality because of the inaccuracy and unreliability of data, the assumptions and proxies used, and the different calculation methods used. The second reason for variation comes from the different processes used in a material's life cycle. One example seen here is that the same type of concrete can be manufactured using either a renewable source of energy or a non-renewable source of energy. Hence, depending on the energy mix used, the emission factor for concrete will vary. Further, our research analyzed the top contributors to emission factor variation across all three materials that we studied. Concrete has an emission factor range of 286 to 483 kilograms CO2e per cubic meter concrete, primarily due to the type of kiln used in manufacturing, and second is the amount of cement used, because cement is one of the most energy intensive components in concrete. Steel too has an emission factor range of 1,160 to 2,390 kilograms CO2e per cubic meter steel, mainly because of the technology used in manufacturing and the total energy mix used. Asphalt too has an emission factors range from 25 to 64 kilograms CO2e per ton asphalt, mainly due to the manufacturing process, that is, the type of dryer used in manufacturing, as well as the manufacturing temperature that produces either hot mix or warm mix asphalt. Overall, the objective of our research was to evaluate the transparency and comparability of emission factors that could be used to accurately measure embedded carbon. A significant difficulty that we faced was the lack of documented data available for the sources used and the calculation methods used. For example, a previously noted EPD provides the emission factor for concrete to be 286 kilograms CO2e per cubic meter concrete. Now this number is only the tip of the information required to accurately measure embedded carbon. Ideally, an EPD should have additional information, such as first, a detailed breakdown of the components used across the processes of a material's life cycle. Second, explain the data sources used as well as the reason for selecting them. And third is outline the calculation methodology used as well as all assumptions used in the calculation. Also, EPDs are self-reported, therefore they must guard against bias. This is especially true since there is no one standard for creating EPDs. Based on this background, EPDs are not a reliable source for emission factors, and hence we conclude that the current state of data available cannot be used by the Port of Seattle to accurately measure embedded carbon in their upcoming construction projects. To remedy this situation, we presented them two actions to increase and improve the data that is available. First is to take a legislative approach by involving stakeholders at the local and state level, as well as collaborating with industry organizations such as the US Green Building Council and other highly sustainable airports such as the Boston Logan International Airport, and they could come together to create a standardized process for publishing EPDs. The second action would require is that they use their purchasing power and to motivate manufacturers to provide higher quality data. And this can be facilitated by creating a standardized data rating system that would assess the quality of data provided and rank it on a qualitative scale of excellent to poor. We believe that with these two actions, we will create a uniting force to put forward the case of measuring embedded carbon. With this, we're super excited to present our findings to our client. Thank you for your time, and open for questions now.
Okay, questions for Shruti, please. Raise your hands.
amongst the different manufacturers that you presented there, since one of your variations is concentration of concrete in the mix, did any of them have varying reputations for quality of their product?
Yes, so we based our research on EPDs, and so we looked at only information available in them. So we do not have any data ratings currently in place that would give us the quality of the numbers that they provide with the data and EPDs. And this was one of the main difficulties that we faced.
Other questions for Shruti, please?
Thank you for your presentation this evening. I'm just wondering, in terms of uniting as many stakeholders to kind of incentivize these cement providers to really take carbon emission data metrics into consideration of their own process, did you consider working with other industries or sectors in order to kind of support that? Or what is the percentage of these materials that goes towards building just airports? I would imagine that would be actually a pretty small
Right.
portion.
Yeah. So we are looking for a policy change with the Port of Seattle, which owns one of the things which they own and operate as an airport. Hence, we look at the purchasing power that the entire port has because of their other aviation and maritime operations. So we feel that we will be able to influence the stakeholders at a state level, such as the Washington State Department of Transportation, to probably put that into their procurement requirements. So we definitely feel that this is something they can do.
Okay, thank you very much, Shruti. Nice job.